Okay, it's a great pleasure for me to welcome Daniel Figueroa. He's a very good friend of mine, but also especially a world expert in particle cosmology. Especially, he has been specializing in gravitational waves, and in particular in trying to predict, as he will explain to us in his talk, the connection between early universe and a stochastic gravitational background. So the floor is yours.
Thank you very much for the introduction, and thank you everybody for coming. It is really a great pleasure to be here in such a renowned institution. So it's really a pleasure, and I hope this is the first time of many to come. So I'm gonna tell you about cosmological backgrounds of gravitational waves. You see I have a multi-colorful title. Not all the colors here are gratuitous. The reason is that I want to highlight, for you to have very clear that I'm going to talk about gravitational waves, but not any type of gravitational waves, but that in the form of backgrounds, and not any backgrounds, but those that are cosmological. So since there are many terms we have to introduce, and I'm well aware that the majority of people here are not working in these topics, let me start by giving some basic clarifications. So we all know that we live in the era of gravitational wave astronomy. We regularly detect signals nowadays with LIGO Virgo network. And this is really a milestone in physics, both theoretically and observationally. And it only took us 1 century, 100 years, to achieve this goal. Okay, so we should really appreciate what this really means. I don't think there are many examples in science that are really comparable to this. What have we learned with these detections in the last 7-8 years? Plenty of things. We've learned about the existence of a certain type of black holes. We have tested the paradigm of black holes and neutron stars. We have tested the paradigm of gravitational theory. So far, no deviation from general relativity. And in general, we've learned that we can observe now the universe with a new pair of eyes. No? And here is what I want to highlight, because this is where I want to focus. We can observe the universe, and I highlight universe because what I want to do with gravitational waves is cosmology. Okay, you can think of doing late universe cosmology or early universe cosmology. The late universe program of cosmology with gravitational waves is very rich, essentially amounts to probe standard sirens, which are going to allow us to measure the Hubble knot or equation of the state of dark energy, cosmological parameters, and so on and so forth. Standard things of cosmology. However, in this talk, I'm going to rather focus in this other branch of cosmology, which is the study of early universe, or in particular, if you want, high-energy particle physics characterized in the early universe. So this is the first observation. This talk is dedicated to particle physics, which is, in cosmology, the part related to the very early universe. The second observation is that we are going to use gravitational waves signal, but in the form of backgrounds. Very important. We are going to be looking at backgrounds. Okay? And third observation, although a bit ridiculous, is that these backgrounds are called stochastic backgrounds. And this is redundant because every background is stochastic. Okay? So I'm myself doing a proactive campaign in the community that we start removing this word from the papers, and we simply refer to them as gravitational wave backgrounds. And the fourth and final observation before we really start is that notice that I'm gonna focus rather on pedagogical or clarity aspects in this talk, and I'm gonna skip technical details. You are very welcome, of course, to ask me about these details if you wish, but the idea here is to give you, the picture, the gross picture, the intuitive ideas, etc. Good. So after we've clarified, what is some of the aspects of this context, let me tell you now really about the motivation of these studies. So gravitational waves can probe the early universe because one reason and only one. So who are PhD students here among the audience? Okay, which is this reason? Inflation. No, more generic, way more generic, What characterizes gravity as opposed to other forces? That is extremely weak. That is extremely weak. And this is this reason. Thanks to the weakness of gravity, when we produce gravitational waves, gravitational wave backgrounds in the early universe, they decouple immediately. and propagate information from that moment. At the same time, this is the reason why it took a century to detect them, because they're extremely weak signals and very difficult to detect. But as positive people we are, no, we know that if we were able to detect these backgrounds, they are going to be a probe of the early universe, which means, during cosmic evolution, they will retain the spectral shape. And for specific processes of high energy physics, there will be a specific spectra, and hence specific signatures that could allow me to probe that different physics in the early universe. Okay, what processes of the early universe can we really measure? Let me first of all introduce you to the early universe to make it clear. Early universe, people, early universe. Okay? Now that you know each other, you should know that by early universe, I literally mean the very first second of the universe. Okay, because sometimes people refer to early universe, for instance, the epoch of decoupling. Okay, no, here we are really referring to the very first second of the universe where high energy scale of particle physics were activated. This implies to consider a period of inflation that one of our colleagues was mentioning, which is just a period of exponential expansion, a period of particle production, which is when all the energy responsible for inflation turns into particles, which eventually thermalize and match with the standard era of the hot Big Bang. Okay. So essentially, the early universe is all these three epochs or whatever it happens before Big Bang nucleosynthesis. Good. Now, how can I really probe the physics of this very unknown first second of the universe? Well, luckily for us, we believe there are a certain number of processes, for instance, the production of curvature fluctuations, or very special processes of particle production, also hypothetical phase transitions, or hypothetical so-called cosmic defects, all of which are very different phenomena among themselves, but they are all characterized by the fact that they depend on a very strong nonlinear dynamics. And why is that interesting? Because when you have this kind of dynamics, then you have a very strong emitter of gravitational waves, a very strong reason to emit gravitational waves. So we are going to look for the gravitational waves emitted by these processes. They will propagate freely, carrying the information of these events in the form, I insist, and I highlight it once again, in the form of backgrounds, okay? Because these signals were produced everywhere in the universe. They arrive today in the form of backgrounds that permeate the whole universe. These are a unique cosmic messenger, which measure in a unique manner the physics, the unknown physics of the early universe. Good. What kind of processes can we measure? We can probe the dynamics of inflation like this. We can probe problems, circumstances of particle production. We can probe phase transitions, and we can probe cosmic strings, cosmic defects in general. We'll see what this is. Okay? So altogether, these are like 4 categories or 4 classification of the different types of sources that produce early universe gravitational wave backgrounds. What about backgrounds from the late universe, once the structure is already there? After all, it is signals of gravitational waves from the late universe that we have measured so far, no? Well, we've measured a lot of signals from individual binaries, but in reality, these signals only represent a very tiny fraction of the many binaries we believe there are there in the universe. Now, most of the binaries are unresolved, at least with our current technology, which means all their signals can add up together in the form of a background. So essentially, the ones that you cannot resolve individually are those that are going to contribute to a so-called astrophysical background. You add them together, they have sufficient strength to really give you a signal, but in the form of a background. So in summary, altogether, the picture is from the early universe, we think there are 4 cases or categories. And from astrophysics, we think there is one very important case, which is the emission of backgrounds from compact binaries. These compact binaries can be made of different stuff, okay? Different objects. Good. So far, so good, I hope, for the motivation. Finally, let me give you a perspective, and then we really start. So my aim with this program is to probe high energy physics, fundamental physics, with gravitational wave backgrounds. For this, we have to try to detect cosmological backgrounds. No? Not any background, but cosmological ones, which are those that come from the early universe. But we know at the same time that there are going to be astrophysical backgrounds. And of course, our detector is just going to measure whatever goes through it. Okay? So the holy grail for us is to detect any of these cosmological backgrounds. However, we know that these astrophysical backgrounds are granted because we already know of the existence of these gravitational wave emitters, the compact binaries, and we know these backgrounds are going to be there necessarily. So the whole game to play is how we can detect any of these cosmological backgrounds of a more fundamental physics behind on top of astrophysical background that from our point of view, they are going to play as a foreground. Okay? Good. So early universe gravitational wave program, essentially, after I gave you some clarification, motivation, and perspective, amounts for studying from a theoretical point of view all these 5 categories. And at the same time, you know, what kind of physicist would I be if I don't confront my theory with observation? At the same time, if I have time in the last 5 minutes, we are gonna also see what is the current state of data analysis, constraints, and, well, potential claim detection for the first time of a background this summer. Okay. Let me start with the theory part. I'm a theorist, so my talk is going to be mostly, you know, dedicated to this. And well, I understand that you guys, or majority of you, are not working on these topics. So I'm going to try to explain them, you know, in their context without entering into technical details. But feel free, if you have curiosity, doubts, or whatever not clear, to interrupt me and ask me. Okay? Not a problem at all. So inflation is the leading framework to explain the initial conditions of the universe. And actually, it simply amounts to postulate a period of exponential expansion at the very beginning of the universe. It explains many properties of the universe. Most importantly, it provides a physical mechanism for the primordial seeds that eventually lead to the anisotropies in the CMB and give rise, trigger the formation of large-scale structures. It produces, or it has, a number of gravitational wave sources, from quantum fluctuations to particle production to primordial black holes or very large scalar fluctuations. We don't have time to cover them all, so I'm just going to give you a brief taste of some of them. I'm going to start with the basic one, the most popular one, which is based on quantum fluctuations. Good. What does it mean, this thing of quantum fluctuations? It means that we are working in a metric theory of gravity, where I have a space-time described by Friedmann-Lemaitre-Robinson-Walker background, and then I have some fluctuations. And the so-called transverse traceless part of these fluctuations, they represent what we call gravitational waves. It turns out that during inflation, these become quantum mechanical objects that fluctuate with zero mean. They have a variance. They have a typical size, this fluctuation. This is just quantum mechanics applied to gravity. Correct. This is fluctuation of the space-time itself because it is a field. Carlos. It is, I mean, the gravitational field here, in this case, the metric tensor, from the point of view of quantum field theory, is a field, and then it fluctuates, you know, that's it. These fluctuations in flat space-time, in the ordinary space surrounding us, they are removed away, but in the context of inflation, they become enhanced. That's the important thing, okay? So essentially, you have this prediction from pure quantum mechanical computation. There is a typical size of these quantum mechanical fluctuations, and it turns out that the amplitude, the spectral amplitude of these modes, of these tensors or gravitational waves, is actually proportional to the Hubble rate or the energy scale of inflation. And hence the importance of looking for this background. Because if you could detect this background, you could infer the energy scale of inflation, something that we don't know in the present time. So how does this background really look like? It has some scale dependence with a very, very small tilt, so essentially it's flat. If we propagate it till today, and I plot omega gravitational waves today, so the fraction of the spectrum of energy density to the critical one, essentially it looks flat. This is the spectral amplitude versus frequency today. If I take into account certain corrections, these ones, then it's a slightly red tilde, but this is very, very minor tilt. What it really matters here is that it's flat, and more importantly, that is way below, even in the best case scenario, of any of the detectors currently working or expected to be working in the near future. So from this point of view, this is not observed. And the only way we could observe it, in principle, could be at the CMB, in the famous B mode, in the polarization field of the CMB.
who is producing the gravitational wave? Because you need a quadrupole moment. So
Yeah.
what is the source of the gravitational wave?
There is no source. This is the interesting thing. This is a quantum mechanical fluctuation of the modes of the gravity field that represent gravitational waves.
So it's something intrinsic to the.
It's intrinsic to having gravity and having quantum mechanics at play.
Okay.
It's very interesting because it's the unique case. Because for any other case I'm going to discuss, there is an active source. But for this one, it's pure quantum mechanical fluctuation of these modes. Because of inflation, these modes redshift away to very outside the horizon. But during the expansion of the universe after inflation, they come inside and they start behaving as a gravitational wave pattern.
So Danny, I always wanted to ask this question. I read many times that this has to do with vacuum fluctuations.
Yes.
But is the universe really hollow? Because you have the inflaton, right? So
Yeah.
is that some type of energy or field that could generate some gravitational
It's the gravitational field itself
Uh-huh.
that fluctuates in vacuum, you know?
Okay.
Of course, if you have a source, then you can add up more tensors, more gravitational waves on top of this vacuum signal, which I'm going to do next.
Okay,
actually.
but the inflaton doesn't add.
No, this has nothing to do with the dynamics of the inflaton, only that there is inflation. Okay, so in that sense, it's
Right.
related to the inflaton, but it's not related to the actual form of the inflaton. This is why this is a generic prediction of inflation.
Okay.
Whenever you inflate, you
Stretch.
take out of the vacuum of your quantum mechanical vacuum these fluctuations, and they become classical and behave as gravitational waves.
Thank you.
This presupposes a particular quantum theory of gravity. It is not given by the same physics as Hawking radiation. It's something more.
This is the very basics of quantum mechanics acting here at so-called sub-Hubble modes. We know it is inconsistent to have a full quantum gravity theory using just quantum mechanical prescription, but at this perturbative level, everybody believes that there is no contradiction and no problem. The problem comes when you go to higher scales, like above Planck scales, and then this quantum mechanical prescription fails. But at these scales, I'm not above the Planck scale, I'm below, and nothing prevents me from thinking that there are quantum mechanical effects in this field as much as in any other field. No? It is an speculation.
Okay.
Yeah, because I mean, so new related to the last figure, you basically is saying that over many order of magnitude, there is no scale. So you expect.
Yes, it's a very important thing of inflation. It's capable of producing a quasi-scale invariant, which means almost the same amplitude at many decades of the scale. But I'm going to change that in a moment if I have an active source, okay? Because unfortunately, unless we are very lucky with nature providing us a very high energetic scale of inflation, we are not going to see this signal in the CMB. Who knows? I mean, but we have a window opportunity for next generation of experiments, obviously, and I understand there are experts here in the room in trying to measure the B mode, but it's not clear, you know, because it depends. It depends on the inflationary model, you know. Yeah. Good or not, because it's not working. Let me now add some more ingredients in my inflationary setup. Let me invoke a symmetry. We theorists, particle physicists, we like to invoke symmetries for everything. I'm going to invoke the so-called shift symmetry, which essentially allows me to couple now my inflaton responsible for inflation to some gauge fields in this particular form. If you know about gauge theories, this is FF dual operator. If you don't worry, it's just gauge fields, okay? And then I add a potential, for some reasons I'm not going to enter, to inflate the universe. If now you study the dynamics of the gauge field in this context of inflation, you immediately discover that there is a chiral imbalance between the two polarizations of your gauge field. And this is because this term is chiral. It doesn't respect chirality, so it breaks chirality. It's like I distinguish left from right in this term. And this is very important because if you know about field theory, immediately you realize here that there is a tachyonic mode. And this implies that one of the elicities, one of the polarizations of my gauge field is going to grow exponentially during inflation. And if that happens, I'm going to have a fantastic source of gravitational waves. Sorry. So there are many consequences from this. I'm not going to discuss them in detail, but just to mention them, this exponential growth of the gauge field produces super large non-Gaussian fluctuations that can be looked for in the CMB. And there are plans to look for this next stage of CMB searches. You can produce also primordial black holes from the fact that you excite so much the gauge fields here. And very interestingly for us, you can produce a lot of gravitational waves, which furthermore, they are chiral. Because their source is chiral, so now the gravitational waves are going to be chiral. One polarization is going to be more active than the other. Okay? Or essentially, you can kill one polarization and be left with the other one. So I'm not going to show you the details of how we do this computation, but at the end of the day, you do your computation. It's been taking us like over 15 years to renew the computation every year with different ingredients because it's very difficult, okay? But I think we are getting there. Essentially, eventually, once you do a computation with a given status of the art of your machinery for doing this computation, the spectrum versus frequency today looks as a blue tilted spectrum that rises up with frequency way above the vacuum case I was presenting before. So now the important thing of this background is that we have an opportunity to detect it directly with direct detection experiments such as LISA. Okay? And this is very important because if we detect this, it's the same as detecting a signal, which is probing directly the particle physics underlying the source, which is this interaction I was speculating.
One short question. These gauge fields, how generic are these predictions? I mean, can you just tune these gauge fields to produce the signal you want, or does this type of signal appear for any gauge
Depends
field?
on the coupling strength, which translates into this constant here. So it depends on the size of this constant. Of course, if the constant is below a certain range, then the signal is here and you don't see it. So no, it's not so super generic, but at least, when you have a source of this kind, you have a window to start probing particle physics, okay? But it's by far, we are not gonna cover the whole parameter space of the case. We wish, Now, I'm just playing around with the ones that are compatible with constraints, So I'm maximizing those values that within a certain range in parameter space are compatible with constraints, so they are not ruled out and still give me a signal. Other than that, no. Good, but the question is even taking all these hypotheses, can we really trust these computations? As I said, we've been evolving in doing these computations. And the problem is the physics of inflation around the moments in which you emit these gravitational waves at these frequencies today, they become very nonlinear physics. This is extremely difficult to tackle. And actually, it can only be solved fundamentally with lattice simulations, like in lattice QCD. And only very, very recently, meaning last year, we've started to produce results in this direction. So remains to be seen that even for the parameter space that we think is observable, whether that's really the case once we do the full thing with the full nonlinearity. That's how difficult these computations are. Well, in summary, the pros of scenarios of this kind are called axion inflation is that they are rooted in concepts of high energy physics like symmetries or axion fields. They have a very rich phenomenology, not only on gravitational waves, they produce primordial black holes, they can realize the baryon asymmetry of the universe, and they are potentially observable. The cons is that the current predictions rely on certain approximations. It's not clear to what extent they are completely valid. And the nonlinear local dynamics during inflation is very difficult to tackle and requires lattice simulations, which are also particularly difficult because we are in inflation. As a matter of fact, the very first lattice study capturing this nonlinear local dynamics comes from my group this very same year. Okay? So we are now working on adding gravitational waves, on adding PBAs, primordial black holes, and all the pheno that people have been working out for the last 15 years. And then we'll be able to answer what is the final parameter space that can be observable or not. Good. What about other phenomena of particle production and independently of inflation or after inflation? There happens to be in the early universe situations where there is like so-called matter field that explosively decays into other particles. And this explosive decays gives rise to a sizable gravitational wave background. Technically, this corresponds to so-called non-perturbative particle production. So it's something you cannot describe with Feynman rules that you learn when you take courses on quantum field theory, that this is something else. This is so-called time-dependent background quantum field theory. So when you study that, you may have a mother field, and you couple the mother field phi to extra degrees of freedom. For instance, a gauge sector, as I did before. In this case, the mother field would be an axion, or to another scalar in this form. In this case, the mother field could be the inflaton or the Higgs of the standard model. Okay? It depends on your scenario. You need Larry simulations in order to capture the nonlinearities of this. Once you do it, you can study problems like this one. I'm just giving you an example. I take a potential to do inflation of the alpha attractor type, which means the potential flattens out in large value, but develops a minimum after inflation, and the field is going to oscillate. And if you couple your inflaton phi to another matter field chi, I call it chi1 here, due to the oscillations, I'm going to induce this time-dependent quantum effects, which is going to translate into particle production of the chi1 field. And essentially, I'm going to develop an exponential power spectrum of the chi fluctuations within a certain range of momentum. Okay? This is called parametric resonance. Good. If there is parametric resonance, then there's going to be a very efficient production of gravitational waves. How efficient? This is the spectrum at the time of production. So you see, I can produce even more than one part over a million in the energy density of gravitational waves compared to the energy density of the system. And I typically, for these systems, predict a single peak power spectrum of the gravitational wave energy density with a height and location, all controlled by this so-called resonance parameter, which depends on the microphysics, the strength of your coupling, the amplitude of the inflaton, and the potential mutual. So this is the outcome, okay? Again, people have worked out this during a decade or so. And now the question is, can I use this to prove particle couplings? Can I really learn something about particle physics using this kind of ideas? And this is a paper from last year, which actually we put out last year, thinking that it would be, revolutionary, but it turned out that people didn't care so much about it. But I still find it very interesting. The reason why it's not so revolutionary is because it's going to require detectors way in the future, but still I want to present you the idea, okay, the underlying idea of how we could do particle physics with this kind of phenomenon. So we have a single peak spectrum of gravitational waves whenever we have a daughter field coupled to the mother field, the inflaton, with a given coupling strength. If I have now two separate universes, and in each of those universes, I have a different daughter species with different coupling strength, then I'm going to produce different backgrounds of gravitational waves, okay? We only have one universe. So instead, in our single universe, I'm going to put two of these daughter fields together. And the question is, what's going to happen? And what comes out is somehow expected, that now I produce a spectrum of gravitational waves that has lower heights on the peaks, but very importantly, the location of the peaks, it's where I was predicting them in first place when I had the single daughter field systems. And hopefully now you see where I'm going to. What about if I have something more realistic, similar as in the standard model, with a family of particle species coupled to my mother field, the inflaton? For the sake of the example, let me just take 3, but you will see the generalization immediately. What's going to come out is that if you have different couplings, you are going to produce different spectroscopic signatures in the spectrum of the gravitational wave background. One peak for each of the coupling strengths that you have to different species. So essentially, we call these stairway signatures. And if you were capable of measuring them, then we would infer the strength of the coupling strength of these interactions from the gravitational wave background measurement. Good. This requires very, very large lattice simulations again, so the whole game has become very numerical, and well, hence why in the community many people are learning these techniques nowadays.
Danny, yeah, quick question. These G factors, these coupling constants, they are supposed to be non-zero for some reason. Is there any motivation for them not being zero? Or
well, it's the same as the standard model, no? When particles exist and they interact with each other, there is a given strength of that interaction, no? This is this strength, these couplings, If they were zero, then particles don't interact with each other. So a way to say they interact with each other is to write a Lagrangian by specifying the functional form of their interaction and fixing the strength by some constant in front. Okay, and this is the whole game we play in particle physics, including in the standard model of particle physics. Okay. Yes.
I understand that now we have matter, no? Because you
Yeah.
say
Now there are
particle-
matter fields.
Okay,
Yeah.
so what is the nature of the gravitation? So where is the gravitational wave coming from? Is because the matter is not distributed symmetrically? What is the reason?
Is the anisotropic stress created by the matter? That's right. So essentially, I went too far, of course, because I'm skipping all the technical details. Is the fact that I create matters in this very excited state, this power spectrum, it's growing exponentially fast within few oscillations of the inflaton. This corresponds to an exponential production of particles. It is that explosive production that is creating the gravitational waves. Because essentially, you are creating a very inhomogeneous distribution, the energy density of these guys, in an exponential manner. And these inhomogeneities, which are fluctuating in time due to the particle production, create gravitational. So this is the source. I'm skipping the technical details.
The motivation for this scenario has to do with reheating in any way?
The
Or-
motivation is that when you finish inflation, you need to transfer the energy from the inflaton into particle species. So if you introduce couplings of this kind, through these effects, these parametric resonance effects, you transfer the energy into this.
And this
particle.
is just a toy model. So to
This is
speak.
just a toy model, but it mimics very well the interactions in the standard model, for instance, between gauge fields and the Higgs. So it's toy to the extent that it's an effective field theory, but it could very well grasp any realistic construction you do. If there's no inflation, then depends what context you are. Okay, if I'm in the thermal expansion of the universe after whatever created the universe, and something else other than inflation set up the initial conditions, still I can have situations, for instance, where a Higgs-like field, like in the standard model, but in an extension of the standard model, also oscillates. It's coupled to a bunch of things and also will create gravitational wave. Here I'm showing you an example where the mother field is the influence, but there are others. Not necessarily. It depends on the relative energy scale of this matter field compared to the background energy density. If there is inflation, no, I mean, I wouldn't say that. This is still model dependent. But no. If there is inflation, you need to generate, because inflation exponentially expands the universe, so you make it empty. So now you need to transfer the energy into particle species. That's called reheating. So reheating in the inflationary paradigm necessarily must happen one way or another. And one way to happen is through this kind of effects. Good. So assuming this kind of effects and this context of reheating in this simplified scenarios, it's still complex because I have multiple particle species. We have this kind of effects. Now, let me show you, for the sake of an example, how this would look like if I were to make a prediction of this kind for the LISA detector with a two-peak signal corresponding to two daughter species coupled to some inflaton guy. So essentially, we injected this in our simulator and we recovered the position of the peaks to few percent, which means now I can engineer inverse this problem into what are the coupling strengths, given the assumption of my interactions. So essentially, these are the theoretical couplings we injected. Let me focus on the first one. And this is how we recover them in the LISA simulator or in another more futuristic proposal, which is Big Bang observatory.
The frequency is related to the energy scale at which this happens, right?
Yes, and here I'm completely cheating because for the scenario I was showing you the results, it's impossible to have the background at the LISA frequencies. It's much more higher frequencies. So what we are looking nowadays is to extrapolate this to lower energy scale models that will give me signals in LISA, which I was going to comment in a moment. So our example should be only taken as a proof of principle, which shows you how particle physics using gravitational wave backgrounds can be really proved, almost at the level of colliders, if you wish. These multi-peak stairway signatures, we think, are going to be generic in a number of circumstances. This is also your question, but one has to work it out, and we are working on this in lower energy scale preheating scenarios or in phase transitions. Of course, there is always the possibility that people would develop sufficiently good high-frequency detectors, and then we could even aim for the kind of backgrounds I was describing directly. But we believe the effect is going to be rather generic, and it could be applied to a different setups that would produce observable signals. We just didn't have enough time since we discovered the effect to really apply it yet. Pros, well, it's clear it can prove couplings of different interactions in a very complementary manner to colliders. It can provide a very large amplitude of gravitational wave backgrounds. This depends again on the assumptions. And the nonlinearities here are under control via lattice simulation because only scalar fields are involved and these are easy to deal with. Cons, these kind of predictions are not guaranteed at all, depends on your modeling, your assumptions. They are typically at high frequencies and they require, in any case, costly lattice simulation, not easy. Good, phase transitions. I don't know how I'm doing because I have the feeling I'm going super slow. Okay, by noon I can do it. Okay, good. Well, I appreciate that there are a lot of questions, but I just lose control of the time. But I really, really appreciate. I prefer to cut some part of the presentation and to have discussion. Okay, so all the questions are very, very welcome. Phase transition. Well, in particle physics, it's very common that when there is a field that has an effective potential with two minima of this kind, if you develop this dynamically, meaning that this second minimum becomes only deeper than the first one, only when temperature drops below a certain threshold, then there's going to be effects that is going to drive my field into this second minimum. This can happen through quantum tunneling, for instance. Okay? This depends on the circumstances. You can also jump through thermal fluctuation. It really depends on the context of the scenario. Either way, this manifests itself into bubbles of this field. Let me call it a Higgs-like field. Could be the Higgs of the Standard Model, could be the Higgs of beyond the Standard Model. You produce these bubbles of these guys. Inside these bubbles, you have the true vacuum expectation value, which is this non-zero value. And outside, you have the zero expectation value, the previous value of the other minimum. These bubbles are unstable. They contain a lot of energy, and they are going to collide among themselves. So when that happens, you are going to produce a lot of gravitational waves. And this is what is called a first-order phase transition. Through the collisions themselves, you are going to produce a lot of gravitational waves. But furthermore, this Higgs field is going to be coupled to the thermal environment, and you are going to stimulate some waves, so waves of pressure in this fluid. And this can even develop turbulence. So from this fluid dynamics, you are also going to produce a lot of gravitational waves. And furthermore, if there are magnetic fields involved, there are magnetohydrodynamical effects that we also expect to source actively gravitational waves. So all these together, you have to put them in any scenario and study it. It's very complicated because all the physics is nonlinear. Once again, requires lattice simulations. Okay? And the status of the art of this particular subfield, which is gravitational wave background from first order phase transition, it has really came to life only since the early 2010s, once people started doing simulation with all these ingredients.
One sentence telling the audience what lattice simulations means.
Sorry. So here we are dealing with field theory. So you should think of your fields as an amplitude, no, like the field of temperature, but here are fundamental fields like the Higgs field, living everywhere in space. Okay. Obviously, I cannot in my computer I cannot simulate all the positions in space, so we discretize space, and that's what we call the lattice. So here we are doing lattice field theory, which is the fields existing only in the lattice sides of my box in the computer. Instead of, it's very similar to what you do when you do Newtonian simulation of particles interacting through gravity, except that there you let them freely propagate to arbitrary positions. Here the positions are fixed, and we let the amplitude of the fields to take arbitrary values according to the dynamics. Thanks. Good. The status of the art is that people study relativistic fluid dynamics and magnetohydrodynamical effects, including turbulence. There is the group of Helsinki, which is taking the lead in these sound waves, and this is the major source actually of gravitational waves as a consequence of a first order phase transition. But there are also the studies of the MHD effects and turbulence. And you see all of this is all very, very recent. People are putting a lot of effort into modeling this as best as possible to be prepared for the era of detectors coming online. This is how the spectrum of a gravitational wave background, one example of a spectrum today, amplitude here versus frequency today, would look like. Is the black line is contributed by three contributions here: the MHD turbulence case, sound waves that ultimately, in this example, takes the maximum height, and also the collisions of walls. So you see here, I have an example of a two-peak structure. You could have a single peak, and so on and so forth. Okay, it really depends on the circumstances. And this is of very interest for the community of particle physics for a reason. Sorry, I was anticipating. I will say it in a moment. Here you have the different peaks, and in this example, it's two peaks, but it could have been single. Okay, and the most important thing is that once again we are talking about potentially observable signals. However, contrary to the other speculative cases I was showing you before, here, not only we can have large amplitudes, although this is not guaranteed, we can easily have it. These are a natural proof of beyond the standard model physics at arbitrary scales, but in particular, for the frequencies of LISA, those frequencies happen to be the scales corresponding to the electroweak phase transition. So in the standard model, there is a transition that separates the electroweak unification into different forces, but that transition is very smooth in the standard model. But if you include beyond the standard model ingredients, then you turn it into a first order phase transition, which manifests itself into bubbles of this kind and all these phenomena. And this is why the particle physics community has jumped like crazy into this kind of studies, because we know this is a natural way, natural because LISA is already approved, of trying to measure what is the nature of the electroweak phase transition in the early universe. Good. The cons. Are the computation realistic? Well, within the last 15 years, they have changed. You know why? Because this is very difficult to model, and there are improvements all the time in our modelings, and there are changes. So at some point, we want to start converging into some formulas we can trust from different points of view. We are not yet there, I'm afraid. Furthermore, people, especially particle physics community, they apply them blindly to some context without knowing what is the context really, you know. They just take the formulas and say, in this context, I have this prediction, but this is not so clear. It can be done like that. And finally, the spectral details actually, at the end of the day, only probe very few parameters of the bubble collisions or of the phase transition. But to invert this problem, the reverse engineering of translating this problem, these parameters, into the actual microphysical parameters of your theory, this is very complicated and there are huge degeneracies. So it's not clear at the end of the, it's going to serve to rule out families, but it's not so clear to determine which electroweak sector is behind a signal if we were ever to measure.
So what is the, this is a complicated question and with many casuistic and so on, but what is the interplay with the LHC? No? We know from LHC that it doesn't seem to be beyond the standard model fields at the electroweak scale, right? So how much these scenarios are constrained by that?
So there are some scenarios which you produce a signal at LISA, which are constrained by LHC. Okay, these are mostly gauge scenarios, you know, because LHC can constrain there like very tightly. But other scenarios, like with higher order operators involving only other scalar sectors, are more easily out of the constraints of the LHC and yet can give you a complementary signal here. Heavy states, yeah, that's right, for instance. Yeah, exactly. Yeah. So essentially, whether they are complementary or not depends, they are complementary by default, but whether they overlap or not depends on the microphysics you choose, and few models in reality they overlap. In those few, probably if we don't detect them in the LHC, we will rule them out and you don't expect them here. Potentially dark sectors, yes, definitely. It includes any particle content beyond that of the standard model. Okay, whether it interacts directly or not with the standard model doesn't matter. That's the model in itself.
So how generic? So this is my question. As soon as you go beyond the standard model, you must have phase transition. Is that right?
No, we wish. No, we wish. No. It's still an speculation. Okay. You could have beyond the standard model particles, and it could be that in the early universe, a strong first order phase transition never happened.
But a famous extension of the standard model have been searched for at the LHC, can produce this first order phase transition. But they haven't been found, so that's...
Yeah. So it is I don't even dare to say it's a likely possibility. I don't know. It's a possibility. And depending on your taste.
Lovely possibility.
Yeah, it's a lovely possibility. But we don't know. We don't know. But the coincidence with the electroweak scale with LISA, that is really there and gives you the chance that if you engineer these possibilities in your BSM extensions, then you are going to be able to constrain those extensions using this gravitational wave technology. Good. Finally, there is a fourth case, which is called cosmic strings. This is a possible consequence when you also have a phase transition. When you break a symmetry, this is what really triggers a phase transition. You start with an initial symmetry, and you end with a simpler symmetry afterwards. And in the process of breaking that symmetry, depending on some mathematical circumstances, it might be that your field develops very special configurations that are called cosmic strings, which are these elongated energy density configurations. Okay, let me not enter into the details. If you want to ask me how that happens later on, I can explain. If you form them, and this is again not guaranteed in BSM extensions, but it can happen in BSM extensions, then there is a lot of phenomenology about gravitational waves, because you are going to produce infinite strings and also loops. So both from the loops and from the whole network of infinite and loops, you are going to produce gravitational waves, and this can be related to grand unified theory. Okay? These are natural prediction, for instance, these cosmic strings in grand unified theory. It's also a natural prediction in axion dark matter theories in certain contexts. Let me give you some taste, once again, of one example, gravitational wave from string loops. So this is how it looks, a simulation of these configurations in field theory lattice simulations. If you isolate one of these loops, each of the loops have a lot of energy, and they are gonna want to oscillate due to this energy. And if you oscillate and you have features, due to gravity, you are going to emit gravitational waves. And Bill Lenkin realized of this already more than 40 years ago. So now if you have many loops in the universe, you can integrate over all the cosmic history of there. So there is a loop number density with given distribution of lengths, and each of them is emitting a given power on gravitational waves. You integrate over cosmic history, and you get what is your background today. So here is the emission of a single loop. And this is based on so-called Nambu-Goto approximation, which is the underlying starting point for string theory. But let me not enter. If you do all that machinery, the spectra look like this. So this is, again, amplitude of the spectrum of gravitational waves today versus frequency today. And for different tensions, which is this parameter here measuring Planck units, the inverse of G, I can have a plethora of parameter space, a very large parameter space compatible with, for instance, observability in LISA. I really have a space to really make a detection here and hence prove this unique beyond the standard model phenomenon. It's observable once again, and that's why there is a lot of interest in the literature. They can be naturally large without tuning anything. They prove specific beyond the standard model physics, like in grand unified theories, but not only. And they have a huge potential discovery in the next generation of experiments coming online, both LISA in space or Einstein telescope, third generation ground-based. The cons, majority of simulations of predictions are based on this Nambu-Goto approximation, which is a theoretical approximation. And even among them, they have different results. So it's not clear how realistic their computations are. And in order to tackle that problem, which is Nambu-Goto versus field theory, people in the community, including myself, my group in Valencia, we've started to try to simulate this with field theory. It's very difficult, but we are doing this. And the first observation is because strings are naturally field theory objects, they are going to emit particles, something that you don't have in the Nambu-Goto picture.
Clarification. So these objects must have decay long ago, no? I mean, they
no.
They can be around.
They can be around. They only represent a small fraction of the energy density of the universe.
Okay, and with that, okay,
They can be around.
They can still consist with observation. Okay, thanks.
They are consistent, even being around with observation. So now, as I was arguing, because these objects are naturally field theory objects, they emit particles. And very recently, what we've done is lattice simulations of isolated loops. It's very difficult to isolate a loop. If you are interested, I can tell you in lunch why it's so difficult, okay? But once you manage to do an isolated loop instead of a whole network, then we've measured the decay, the natural decay into quanta of this guy versus its length. Okay, we've measured with many parameters, and we've measured at the same time the emission of gravitational waves. So for the first time now we've captured the emission of particles and the emission of gravity, of particles and gravitational waves. And our result is very depressing, which is the power emission of gravitational waves versus particle emission is very suppressed, the vacuum expectation value to the Planck mass. And the vacuum expectation value nowadays cannot be larger than 10 to minus 5, the Planck mass. So this is a 10 orders of magnitude suppressed. It's very bad. But more to be seen soon. Finally,
Before you move on, you said that the existence of strings has not been discarded from observations. Is that including CMB observations? Because
that includes CMB observations. So from CMB, what you put is constraints, upper bounds into what's the maximum tension you can tolerate for them to contribute into CMB anisotropy. That doesn't rule them out. It simply says that you cannot have them with a given tension above a certain threshold.
Okay.
The whole universe, massive. I wouldn't talk about a mass of them, but they have an energy density or an energy surface, if you want, which can be very large, because typically the width of them is the inverse of the mass scale of the problem. And if you are in GAT, this is the inverse of a GAT particle width, so very, very, very concentrated energy, Good. So finally, remember there are the astrophysical backgrounds, the astrophysical binaries. There is a distribution of them depending on mass and spin for different types of compact binaries, for instance, for black holes, neutron stars, and for white dwarfs. And you need to calibrate all these mass and spin distributions based on observations and simulations altogether. And if you are capable of calibrating these distributions, for instance, for black holes of solar mass type, the ones observed by LIGO Virgo, this has been done with certain accuracy, still to be improved. And then you can compute, in this case, because there is this calibration, what is the expected stochastic background from the unresolved binaries for different experiments. We've recently done this for the LISA collaboration with these collaborators here. And this is the result. This is the sensitivity of LISA, and this is the background, the realistic prediction of the background. And if I simplify for you to see it more clearly, is these other solid lines here. Or if we just take the mean value and the variance, essentially it will look like this. Okay? This kind of variance. It's completely observable within the LISA sensitivity. And hence we know it's a guaranteed foreground, because this is based on the physics we already know as inferred from the distribution of black holes from LIGO Virgo. And other teams have done the same computation, and luckily we pretty much agree. Yeah. Okay, finally, I'm going to attempt in 5 minutes to conclude by giving you very fast over the observations overview. So data analysis is becoming, obviously a very important aspect in this business, despite the fact that the majority of people we were working on this, we were theorists and we knew nothing of data analysis, okay? So we are teaching ourselves, as fast as possible, this kind of thing. So only 4 years ago, we developed the first automatized analyzer capable of reconstructing an arbitrary spectrum for an experiment like LISA. Until then, we were doing that by eye. Now we've done it very recently with machine learning techniques. So we've improved a lot, because now in a microsecond, we can do Bayesian parameter estimation. And this now can be extended not only to LISA, but to any other experiment, as long as you can parameterize the noise. People are playing to combine experiments, because this can help you, obviously, to improve parameter constraints. And we are also dealing with the problem of reconstructing fundamental signal on top of a foreground. Okay, something probably is very familiar to CMB people here. Now we are starting to deal with that problem here. Constraints on existence of backgrounds. Until before June 2023, this is the CMB constraint. This is the non-detection of B modes, essentially. This is the spectrum versus frequency. And the non-detection of B modes translates into this. This is the constraints from PTAs before announcement was made a few months ago. And this is constraints from LIGO Virgo, because they haven't detected any background. The perspective for the next 2 decades or so is pretty good. there's so much interest in the community, in physics community in general, that people have started working out a bunch of different experiments that are going to cover all the otherwise empty plane here. No, this is very nice because we are going to have a great opportunity to discover gravitational wave backgrounds there, or to rule them out. In the next 34 years, there is even some predictions already, or some proposals of what could be the way to go in order to even improve sensitivity. Okay? But still very futuristic. And finally, let me comment very briefly, 1-2 minutes, on the potential evidence. Maybe the elephant on the room, because probably many of you are aware that, well, I hope everybody's aware that Pulsar Timing Array Collaborations in June this year has announced evidence for a stochastic gravitational wave pattern. This is because they've measured an angular correlation between different pulsars they've been monitoring. And if the shape of this angular correlation verifies a very specific pattern called the Helins down, this implies that the light that is traveling from these pulsars to you is traveling through a background of gravitational waves. So essentially, the 4 collaborations have provided a strong evidence of the existence of a background of this kind. I wouldn't say this is discovery, because depending on the collaboration, this goes from 2 to 4 sigma. The Chinese claim 5 sigma, but also it's not so clear how they did the analysis. In any case, this is good news, because it's the really first evidence whatsoever of any time on the existence or potential existence of a gravitational wave background. And of course, the interpretation of this signal, very likely it is due to supermassive black holes. This is why the supermassive black holes also orbit, the center of galaxies, when galaxies are forming, also orbit around each other, and they emit gravitational waves pretty much as the compact binaries we are measuring nowadays. But there is, of course, also the possibility, more speculative, that this could be due to one of the cosmological signals I've been presenting to you today. This is, it turns out to be from supermassive black hole binaries, this is an astrophysical signal that is expected. If it turns out to be something from the early universe, you have to realize that this is literally a revolution, because it would be the first time that we really start probing the very first second of the universe directly. Okay. How we are going to try to distinguish these 2 possibilities? The key point, I think, is going to be the anisotropies. They are like crazy looking for them in the collaborations. And actually, for the meeting that is going to be held here in the next 3 days, we have invited one expert from one of the collaborations to tell us about the search for these anisotropies of the astrophysical signal. For the early universe possibility, the key is going to be the spectral shape. If the data improve with time, which it has to, because you accumulate more data, you'll be able to measure better and better the spectral shape, and eventually we'll be able to remove one possibility from another. Good. Conclusions, my very last 30 seconds, even since I'm a bit time, let me jump directly. Yeah. There are 5 categories of early universe. Okay. All the cases that people have worked out can be always fit within either of those 4 categories. And then there is different families of black holes, neutron stars, white dwarfs, and combinations that can give you an astrophysical signal. If we detect something from the early universe, this is literally opening a new window, really, to the earliest moments of the universe. And it means to reach energies way above terrestrial means, very important, in order to probe fundamental physics beyond the standard model. Typically physics that actually is otherwise inaccessible, because many of these backgrounds cannot be proved their physics with colliders. Okay? Only very few examples of the first order phase transition kind. And this is possibly as close as we are going to get to the origin of the universe. But furthermore, not only this is a new window to the universe, this could be as revolutionary as the CMB discovery, and it's complementary to colliders and even beyond, okay, and possibly the only way in many cases. But even otherwise, if we never detect any of these primordial backgrounds, but we detect astrophysical signals, still this is good, because we are going to produce very stringent constraints on beyond the standard model scenarios, ruling out really a lot of early universes. And that's why the signal from PTA, just because it's there, it's considered the dawn of early universe gravitational wave. Thank you very much. For your attention.
Great. Thank you. Thank you, Danny, for this great summary about gravitational wave backgrounds and questions.
Okay. Thanks, Daniel. Very nice introduction for, I think, most of us that don't know anything about this. So let's assume the universe is super boring and we know basically all the physics except for a few things. So I think that you have tried to summarize this in your last slide, but so let's assume inflation is not there.
Yeah.
There's no phase transition. There's no cosmic strings.
Yeah.
So what do you think would be something that we could learn from the very early universe? Imagine that we have the technology and we can measure it. So for example, this particle producing is something that we should still, because we know particles have to be produced at some point. So what would you think it would be the very least thing that we would learn from this?
Well, the very thing we will learn if in the next 2 decades we don't probe B modes in the CMB and we don't see any of these signals, is that the energy scale of inflation, if inflation ever happened, has to be sufficiently low such that we are not detecting. That's already a piece of information. It's putting to lower grounds what's the energy scale of potential inflation. The second thing is that first order phase transition didn't happen, and that's going to impact in a number of families of beyond the standard model scenarios. The third thing is that if we don't detect cosmic strings, we are going to close to a very narrow parameter space between the capabilities of colliders and these cosmological capabilities, the range of space that is not probed. On the one hand from gravitational wave backgrounds, on the other hand from colliders, because they are really coming as a sandwich like this. And if we don't detect them, still there is some parameter space compatible with both LHC and both non-detection in gravitational wave background experiments. But it means that for next generation of experiments, hopefully we'll close that gap. And then we'll be able to rule out that, so a most boring situation will be that we start ruling out many things. That's always information. Because right now the difficulty is that to constrain BSM, we need signals to rule them out. And for that, you need the technology to be capable of detecting these things. And this is precisely this era of gravitational wave detectors.
The physics that we know already.
Yeah.
So imagine that we know everything. So still we expect to measure any early universe gravitational wave. So if we know everything right now,
well, what does it mean with the physics we know?
The physics that we know, standard
model, we don't expect nothing of this.
Yeah, but the most okay, we know there's dark energy, dark matter, and so forth. But I mean, there are things that we know. Okay.
Still, so by know, it depends what you mean by know.
Okay, by know I mean that we have at some point particles were produced, because we think that there was a hot Big Bang.
You see, we don't really know that. The point is, we know the standard hot Big Bang scenario. It's inconsistent due to causality, for instance. And that's why people introduce inflation. It's a speculation to correct for that. But it is true. That's not a proof that inflation really was there. So all we can do is play this game of assuming it was there and see how different ingredients in the assumption can give me rise to observables. But it is possible that even within all those assumptions, still we see no signal, So it's very difficult to answer your question, It's really very difficult. Within the standard model as it is, there wouldn't be any observation. On the other hand, we know the standard model is incomplete. Sure. Requires dark energy, requires dark matter, and very likely, if not inflation, something else, because the inconsistency of the hot Big Bang theory is clear. So.
Thank you very much for the very nice presentation. So maybe I missed something. At the beginning, you said that the responsible for the generation of the B modes are the quantum fluctuation of the background. Then you explained another mechanism that is the particle production that also generate gravitational waves. Is this kind of mechanism also in some way linked to the generation of B modes?
I mean, technically, yes, but in practice, you won't be able to see them. I'll explain you why. Because it has to do with the scales. Okay, So look, this vacuum spectrum that is quasi-scale invariant extends all the way to here, but also all the way here to CMB scales. Now, in these scenarios of particle production, I want to respect CMB constraints. So essentially, your couplings are chosen in such a way that the particle production only starts towards the middle stage and late stages of inflation, not 60 EFOLs before the end of inflation when the scales of the CMB cross the Hubble radius. That means that I only start seeing these effects at frequencies that correspond to scales much, much shorter than the scales you can probe in the CMB. So these kind of extra tensor modes, they wouldn't affect the CMB scales because the CMB scales is here and they are completely suppressed there. See.
Thank you. Actually, this was my question. Raul's question was my question. But so in some way, CMB observations or constraints are actually constraining all these mechanisms that you've been describing.
Totally,
right?
totally. I mean, B modes to begin with give me the constraint of what is the upper bound on the range scale of inflation that I have to take it into account in any construction. Okay? There cannot be higher energy scale than what B mode constraints give me nowadays. Unfortunately, those constraints are still very weak in terms of energy scales, but you know, of course, you have to take into account that those constraints. And the fact that this guy come up here also has to do with at CMB, I have to respect non-Gaussianity constraints. And if I tolerate a bigger coupling, this effect is going to come earlier and it's going to induce non-Gaussianity stronger at CMB scales, and then it would be ruled out.
All right.
Okay? So for this particular scenario, to respect CMB scales, it means that it only happens at these frequencies. For other scenarios, now we are working out the possibility to have this kind of effects at CMB scales. But then once you have them, it has to come down.
Right.
You need an extra mechanism, because if it doesn't come down, then you violate everything and you don't end inflation.
Okay.
But it's possible.
More questions for Danny?
Do you have an opinion on whether rotating neutron stars such as pulsars could make detectable gravitational wave emissions?
By them individually, you mean?
Yeah, by the rotation. I mean, there's been speculation that if they have certain oblateness, they could act as gravitational wave sources. Not like in a binary system, but I don't believe there's been any detection or.
So you are talking about emission by the deformity of these neutron stars.
Yeah, exactly.
I don't have the expertise to comment.
Okay, sure, no problem.
If there are no more questions in the audience, I see no chats. I think you did great. I think you did a great summary.
Great going
So
over
let's
time.
thank Danny again.